Okay, so related rates, just a reminder of where we were last time. We talked about the fact that you first need to read the question, right? That's not in here. And then you need to determine what's given, write as variables. That was a lot of the homework last night, was kind of decoding the paragraph to figure out what information am I actually being given. Then you needed to write an equation that related the variables. So that was part of one of the second assignments I think that you had to do last night. And so you had to determine what was given. And then you had to come up with an equation kind of relating that information. Then the next thing you do once you have that is you differentiate. So you take the derivative with respect to whatever the problem has. A lot of times it's time, but not necessarily. That was kind of the third Khan Academy you worked on, where it wasn't word problems. It was just taking derivatives using implicit differentiation. And then step 4 was to substitute in the given information in order to solve. And then we use the units as applicable. So this is the problem we did yesterday, a circular pool of water. If you guys remember, we were given information about the fact that that circular pool of water was expanding at a rate of 16 pi inches squared per second. The inches squared is what told us it was a change in area. And then the seconds told us that it was with respect to time. And so we set up our given. We knew that because it's talking about a circle, area, and radius, that the equation that related that information was a equals pi r squared. We had no constants that we could plug in, so we just took the derivative, substituted in our given information, and solved, and then used units. So this is a question from Khan Academy last night. I know we started the ladder problem. We'll come back to that in a second. So I want everyone to write this one down. This was one of the most missed problems on the third quest last night. This says x cubed minus y squared equals 7. It gives us that dx over dt equals 0.5. And it asks us to find dy dt when y equals -1. So this is not a word problem, and there's a bunch of these kinds of problems on your quest this week too. So some of them on your quest are word problems. Some of them are just like this, just practicing kind of the implicit differentiation and plugging in given information. Okay, so there's a couple things I would do here. First, I would add this find when. I would add that over here to my list of information. So like it wants us to find dy dt. I think it's helpful to identify what it is you're looking for over in that list of information. And then it also gives us y is equal to -1. So I'm going to add that to my list. There's one additional thing I'm going to change about this, which is the 0.5. It is almost always going to be easier to use fractions. A lot of these questions you're not going to be given a calculator for. And so you want to try to make the math a little easier for yourself. Multiplying by 0.5 is just harder than multiplying by 1/2. It's just things cancel out a little easier, or easier to see when you think about 1/2. 0.5 is not a big deal, but if it was like 2/3 or I don't know, 1/4, sometimes it's easier to actually think about the fraction. Okay, so we are going to start with our given equation. We already have the equation. We didn't have to come up with it. It's x cubed minus y squared equals 7. The next thing I'm going to do is take a derivative, because all that given information is giving me stuff about dx dt. It's asking me stuff about dy dt, which means I need to take the derivative with respect to t. Let's go to Luis. What would the derivative with respect to t be equal to? Luis Reyes? Hello?
Hear me?
I can now. Go ahead.
So would it be 3x squared dx over dt minus 2y dy over dt equals 0?
2y dy over dt equals 0. Absolutely perfect. Great job, Luis. Okay, so we took the derivative of each portion. We remembered our chain rule, right? Our inside function is really x. So we need to multiply by the derivative of that x, which is dx dt when we're taking it with respect to t. Same thing with our y. So we get 2y really to the first power, and then our y is our inside function, so we multiply by the derivative. A thing a lot of guys forget here is they'll accidentally write like an equals 7. They'll just forget to take the derivative of the constant. So don't forget that the derivative of a constant is always 0. Okay, from here, Dennis, what would you do next?
Okay, I would plug in dx over dt.
Okay, so you can plug in dx over dt. So we get 3x squared times dx over dt is 1/2. And then minus 2, I'm assuming you also want to plug in the y?
Yeah.
Okay, so 2 times negative 1 times dy dt. We don't know dy dt, and it equals 0. So the issue with this problem, and I think the reason this was one of the most missed, is because there's 2 unknowns, and we only have 1 equation that we're solving. Okay, so I wasn't given x, and I also was not given dy dt, and I need to find dy dt. Secretly, because of the information that you were given one of those pieces of information. Does anyone have a way to solve for one of those missing things?
We were given the value of y, so we could plug in -1 into that x cubed minus 2y equals 7, and that would give us the value for x.
That's exactly right, Gus. So sometimes you actually are given more information. It's just not spelled out correctly. So if they give you an equation with 2 variables and they give you one of those variables, they are also giving you the other variable. So it's exactly as Gus said, we were given y equals -1. We have to go back and use our original equation to find x. So we would get x cubed minus our -1 squared is equal to 7. Then we get x cubed minus a positive 1, right? Because that's -1 squared. It's -1 times -1, but it's subtracted, is equal to 7. We can add the 1 to both sides. We get x cubed equals 8. And then x is equal to positive 2. So we actually were given that x equals 2, just not explicitly. We had to find it, but we had enough information prior to taking derivatives in order to do that. So that is going to go in for our x value there. Okay, so Aiden Lynn, what does my equation become?
It would become 3 times times 2 squared times 1/2 minus 2 times 1/2 dy over dt equals 0. Or you can
wait, minus 2 times what?
Times -1 times dy over dt.
Perfect. Equals 0. Okay, why don't you go about solving this for us, Aiden?
Okay, so you could first, I guess, simplify. So the first part would be 3 times 4 times 1/2, so that would be 6.
Okay, perfect.
And then it would be plus 2 dy over dt equals 0.
Keep going.
So then you would get 2 dy over dt equals -6. So then dy over dt equals -3. If you divide 2.
Fantastic. Perfect. And I don't really care if you show that divide by 2 step. Okay, so dy dt equals -3. Okay, this was one of the most missed problems. Really, all this is implicit differentiation, right? Plugging in information. But the trick here was that we were given more information than we thought we were actually given. Okay, any questions on that problem?
Yeah, Ms. Tosher, I have a question.
Yes, go ahead.
So I watched the Khan Academy video on this last night, and
Sure.
it did something where it said dy over dt, or whatever you're solving for, equals dx over dt times dy over dx. And then once you got that you have the dx over dt value, and you solve for the dy over dx value and then multiply them together. Is that something that you don't want us to be doing, or is it scary, or whatever?
I think that way is more complicated to think about, honestly. So that's a valid approach. That's kind of the definition of chain rule if you're using that method, the way that they're going about it. And that's going to kind of come up in some stuff we do later. It's just a little more complicated than this approach. This
Right.
approach, all you need to know is how to do implicit differentiation. That's
Okay.
it. And so that's why I don't, like, you can do it that way. I just don't think it's the easiest way to do it.
Awesome. Thank you.
Yeah, of course. Any other questions? Okay, we're gonna go back to this ladder problem. We're gonna start this problem over because I know I was racing at the very end of that class to try to get this one going. So again, we're given a 25-foot ladder. It's leaning against a wall and sliding toward the floor. So again, I have a ladder sliding down the wall towards the floor, where the top of the ladder is like perfectly against the wall and the bottom of the ladder is perfectly on the floor, and there's frictionless environment because everything is perfect in calculus. Okay, if the foot of the ladder is sliding away from the base of the wall at 15 feet per second, how fast is the top of the ladder sliding down the wall when the top of the ladder is 7 feet from the ground? What a mouthful. I would write on your problem, or on your notes, the ladder problem. I would like have those words, the ladder problem, just because there are so many kinds of ladder problems and they're very similar and they're very common. And you can look up a bunch of videos on YouTube for some extra help on these. Okay, so sometimes it's helpful to draw a picture to visualize. So that's where we started last time. I drew just kind of like a wall here, and I drew a ladder, right? And I labeled those sides so that it's helpful for me when I come back and I'm trying to evaluate, like, what did that label represent, that I can come back to that. So I called the base here X. And what I mean by that is this like distance here from the wall to the base of the ladder. I'm calling that distance X. Anytime you're dealing with a triangle, it's helpful to call the horizontal component X. It's just going to be consistent. You're going to do that in physics too, if you haven't already. Okay. Then I'm going to call the vertical component Y. And again, that is just this length here. So whatever the length of that ladder against the wall is. So that length is changing because the ladder is falling down the wall. Okay. Now we have a ladder that's sliding out. So I like to show an arrow for that motion that's happening. And that's represented by our dx over dt. So again, that's a derivative of x, meaning a change in x with respect to time, right? So x, because the ladder is sliding, x is getting bigger as time progresses, okay? And then I have an arrow going this way. You'll notice they're not both going out. We don't have a magic growing ladder, right? So as it falls and the length of the horizontal component grows, the length of the vertical component gets smaller. And I'm gonna call that a dy dt. I don't have any values associated with that picture at this point. You could if you wanted to. I just think it's very helpful to have a picture for a problem like this so you can visualize what's going on. Okay, now I'm going to write down some given information here. So I have information about the length of the ladder. It says it's a 25-foot ladder. I'm gonna call this side my R. You could call it something else if you want, but for us to be consistent right now, let's just use the variable R so we're on the same page, okay? And R is one of my given information, and that's 25 feet. And I would put a star next to this and write the word constant. Anytime you have a constant, it's important to identify that in your given information because we're gonna plug constants in before we take a derivative to make our derivatives a little bit easier, okay? Now this is a constant because it's not a growing magic ladder. It is always a 25-foot ladder. It never changes its length, okay? Then it says if the foot of the ladder is sliding away from the base of the wall. So what is that phrase talking about, Noah? The foot of the ladder sliding away from the base of the wall. What's that variable? Noah?
I think he's having some technical difficulties with his mic.
Dang. Nathan, you want to answer that one for us?
For the X?
So it says if the foot of the ladder is sliding away from the wall at 15 feet per second. So what information would that be?
The dx over dt.
Perfect, exactly right. So we're talking about this part of the ladder is sliding away from the wall, right? And it's a rate because it's in feet per second. So that's our dx over dt is equal to 15. And again, I'm going to leave my units off of my list of information to start. And then it wants to know how fast is the top of the ladder sliding down the wall. So what information is that, Brian, that we're looking for?
The height.
So in terms of our variables, what is that? So it wants to know how fast, so a rate, how fast is the top of the ladder sliding down the wall? So what information are we looking for?
Sorry, can you ask the question one more time?
Yes. So we're looking for how fast, so that indicates a rate. How fast is something per time is the top of the ladder sliding down the wall? What variable would that be referring to?
dy over dt.
Perfect. So dy over dt is what we don't know. I'm going to put equals question mark and a little box around it so I know that's what I'm looking to find. And then it says when the top of the ladder is 7 feet off the ground. Neil Patel, what is that last piece of information?
Just the y.
Yeah, y, perfect. It's just y. It's not a rate. It's just saying when y is 7. So there's a moment in time right? When y is 7. Y is not 7 forever because the ladder is constantly moving, but there's a moment when that height, that y value, that vertical component is equal to 7. Okay, so now we have our list of information. That seems to be all of the information we have. Eli, Reed, the next thing we're going to do is come up with an equation that relates this information and the scenario. So in this situation, I have a triangle. It's a right triangle. I have an x, a y, and an r. Okay, what is an equation that you can come up with, Eli, that relates that information?
Pythagorean Theorem.
Perfect, exactly right. What would you write for your Pythag?
25 squared.
No, hold on. Start out with the general equation first. You're not wrong, but let's start out with our general before we plug in stuff, but you're not wrong.
And r squared equals x squared plus y squared.
Perfect. Okay, so, and then Eli's exactly right. We're going to plug that 25 in, but I think it's helpful to have the basic equation first. Okay, so we're going to plug in our 25 right off the bat because it's constant. Always plug in your constants first. You'll notice that saves us from getting like a dr dt, which I don't have any information about. So it wouldn't be helpful to take that derivative. So we get 25 squared is equal to x squared plus y squared. Okay, now there's two different things you can do from here that are both correct. Gus, what would you do next?
Well, I gotta somehow insert that dx dt into our like what we have right now, but the x squared plus y squared. So I'd probably like differentiate.
Perfect. You'd take a derivative, right? That's exactly what you should do. So go ahead and take that derivative for us, Gus. On the left side, we have 25 squared. So a number, 625. What's the derivative of that number?
Derivative of 625 is 0.
Perfect. So again, that made that derivative a lot easier because now it just goes away. Now it's just 0 instead of a 2r dr dt or something else. Okay. How about the derivative of the x squared? What's that equal to?
2x times dx over dt.
Good. Keep going.
And then plus 2y dy over dt.
Okay, fantastic. So there are 4 variables in that equation right there. Got an x, a dx dt, a y, and a dy dt. I am looking for dy dt. I am given dx dt and y, but I am not given x. Conrad, what do I do to find x?
You would plug in all the numbers for the original r squared equals x squared plus y squared.
Fantastic. That's exactly right. So this is like the previous problem we just talked about. So sometimes I'm actually given more information than it appears that I need to use in order to plug into my derivative. So we're going to use that original equation and we're going to plug in our r and our y to figure out what x is at that moment. Because at that moment, we can figure out what x is. So again, we get 25 squared is equal to x squared plus our y is 7, so 7 squared. So that gives me 625 is equal to x squared plus 49. We get 625 minus 49, which is 576. And then we're going to take the square root of that value. Square root of 576 is 24. So we get x is equal to 24. Now, technically, we had an x squared. We get a plus or a minus. Conrad, why is it only the positive 24?
Because distance can't be negative.
Distance can't be negative. It doesn't make sense in this problem if x was equal to a negative value. Okay, so we get x equals 24. That's going to actually go in to our list of given information. We can add that to our list. So you could have found that first if you wanted to, and then gone back to this equation that we did over here in yellow and then took the derivative. Just be careful not to try to take the derivative of like this equation, right? Because y was not constant. And so if you take the derivative of that equation that I just circled, you're going to get to a wrong place. Okay, so we're back here to our blue equation, 0 equals 2x dx dt plus 2y dy dt. George, what do you want to do next?
Start at plugging in some of the values. So
Good.
you can have 0 equals 2 times 24 for x times 15 plus 2 times 7 times dy over dt.
Good. Okay. Now, obviously, we're going to multiply some of these things out and then we're going to divide. My suggestion is to actually isolate all that stuff first. So like, I'm going to need to subtract whatever number this is. Sometimes these are going to be calculator active problems, sometimes not. You know, my algebra 1 guys can take this and do this by hand. It just takes a little while, but they could do it. Okay. But again, I know that I'm going to be multiplying, subtracting and then dividing in order to isolate dy dt. Sometimes it's easier not to multiply it out first. So even if I don't have a calculator, what I think is sometimes easier is to actually just take subtraction to get rid of that 2, 24, and 15, and then use division to get rid of the 2 and the 7. And here's why. A bunch of stuff is going to cancel out, and it's going to make the multiplication easier. Okay, if this is on the no calculator section, you want faster ways to try to solve this. So you can see that I can cancel out the 2's. Like, I don't want to sit here and do 24 times 15, to be quite honest with you. Okay, 24 divided by 7. Anything I can do with that? Nope. So we could get rid of the 2's at least. Looks like we're still going to have our 24 times 15. So at this point, yeah, you can go ahead and type that in your calculator if you want, just for the purposes of time. We get 360 divided by 7 is equal to our dy dt. I'm going to put that on the other side. So dy dt is equal to 360 over 7. Okay, but this problem had units on it. Yes.
It should be negative.
Oh, thank you. Thank you, thank you, thank you, thank you, thank you, thank you, thank you. Okay, negative, where did my equal sign go? 360 over 7. Fantastic. And you would notice that it needs to be negative in a second when we describe this. So let's talk about units first. Charlie, what would the units of this be?
It would be feet per second.
Feet per second. So it's going to be the same kind of units that we had for our dx dt, right? If you look back at our dx dt, we had 15 feet per second. We're going to have negative 360 over 7 feet per second. Okay, Matt Graff, why did we get a negative value for this rate? Can you explain what that negative means here?
Because the y position, it's moving down, so it's getting closer to 0, like, or it's sliding downwards.
That is a physics answer. Matt, have you taken physics?
Okay, I have. Well, I was gonna say because the change in y.
No, it's okay. I'm looking for a relationship between derivatives, right? So what's true when I have a negative derivative? What did that mean about my original function? If I ever have a derivative that is negative, what did that mean my original function was doing, Matt?
I'm just gonna guess that it was probably negative to begin with. I don't really know.
That's okay. Does anyone know the answer to that question? I know it's kind of a backwards way to ask it. If my derivative is negative, what was my original function doing?
Decreasing?
It was decreasing. Exactly. You guys remember when we were doing those graphs and we looked at graphs that were decreasing, we said, oh, that means the derivative is negative. So if we go in the reverse, if the derivative is negative, that meant the original thing was decreasing. So Matt's explanation is correct, but what I was looking for him to say is the y is decreasing. That's why dy dt is negative, because y is decreasing, okay? Sometimes we'll have something where it's moving to the left, but maybe it's getting bigger. And so it's just, you gotta be careful of some of that ideology of moving toward the origin and those kinds of things, okay? Does that make sense to everyone? Excellent. Any questions on this problem? Okay, let's go to this next one. Okay, so it says a spherical balloon is expanding at 60 pi inches cubed per second. How fast is the surface area of the balloon expanding when the radius of the balloon is 4 inches? I want you to take a second. I'll leave this up here, read it again, and I want you to try to write down what your given information is. One thing to note on AP Calculus, if it's a hard equation, so like a circle we think is easy, a rectangle we think is easy, a cylinder actually we think is easy because you can figure it out. But if it's something like volume of a sphere or surface area of a sphere, we give that to you. Okay, so you don't have to memorize those random equations. Okay, so read this again, try to figure out your given information. and also what you're trying to find. All right, Nauman, what do you have written down?
I have the radius at 4, and then the spherical balloon expanding it, or that it's expanding at 60 inches cubed per second.
60 pi inches cubed per second. So what variable would you put that with? The fact that the spherical balloon is expanding at 60 pi inches cubed per second. What would you call that?
Is it would it be dx over dt or dy?
You're close, except the thing that an inches cubed is, Nauman, what's an inches cubed going to represent? What kind of information?
Volume.
A volume. So not a dx or a dy, but a
dv over dt.
dv, perfect. So it's a volume change, so we're going to call that a dv over dt. And don't forget your pi. Pi is not a part of the units. Pi is part of the number, so 60 pi. Okay, so our dv over dt, that's the rate of change of the volume over time, is 60 pi. Okay, and then it says, Nauman, how fast is the surface area of the balloon expanding? So it wants a rate of change of that surface area. So what would you say that we're looking for here?
Would it be like, what's the variable? Would it be like d something over dt?
Yes, it is. And here's the deal. Some guys are going to want to write like this, DSA, surface area. You can only pick one variable up there. And so in the given part of the problem, you'll notice they just called A equals 4 pi r squared. That represents our surface area. So you should probably just use A. That one's a little more challenging. Like if you want to call it S, that's fine. But because they already specified it as an A, we're going to call it an A. But yes, it's a D something over DT. So we just had to come up with that information. And we don't know that. That's the thing we're looking for. Okay. All right. So this one's a bit more challenging. We have two equations. They gave us two off the bat. They said, here's the volume equation, 4/3 pi r cubed. Also, here's the surface area equation of the sphere, 4 pi r squared. Now, we know we're going to need a dv dt and we're going to need a dA dt. Okay, and there's a couple different ways to do this problem. We're gonna just take one route, but there's many different routes you can take. If I know I need a dv dt and I know I need a dA dt, that means I'm gonna have to take the derivative of both of those equations. Does that make sense to everyone? Like in order to get a dv dt, I gotta take a derivative of the left one. In order to get a dA dt, I need the derivative of the right. Okay, so take a second, write down what you think the answer to those derivatives is. So take a derivative of both of those equations. Give you about 30 seconds.
Ms. Toshner?
Yes, sir.
Would it not work to like set like manipulate the left-hand equation so that like 3v over r equals 4 pi r squared?
So exactly, that's one of the things you can do. And we're going to talk about that and if that's helpful or not here. And there's some ways that you're going to see that. That's a great thought though. For now, I just want you to take the derivatives of both. But yes, we're going to talk about exactly that in just a second.
Okay.
But for now, just take the derivatives of both. Good eye. Good eye, good eye. Okay, let's go to JJ. JJ, derivative of this first one.
Let's see. So I put 4 all over 3 pi was a constant. So
hold on. What's the derivative of v?
Isn't that just 60 pi?
So you need to write it as a variable first. I need just like what it is in general. So don't skip those steps. So the derivative of v is what?
Would it just be dv all over dt?
Yeah, perfect. So don't plug in that stuff yet. Like actually take the derivative and show those variables, that first step. Okay. And then when you took the derivative of the next thing, what'd you get, JJ?
I got 3r squared times dv all over dt.
Okay, so what happened to your pi?
I saw it as a constant, so I took it out. Or do I leave
Okay,
it?
so remember, if I have a constant like 3 times x squared, that constant doesn't just go away.
Okay.
Right? So what happens is I take this and I multiply it by the constant. So I get like 2 times 3 times x raised to the first power and then times whatever the derivative of x is, depending on what I'm taking it with respect to. Okay, so what you should be doing here is you should be taking this 3, multiplying it by that whole constant. So 3 times 4/3 pi. Okay,
so 4 pi.
And then times r raised to the 2nd power.
Times, would it just be dr over dt?
Perfect, times the derivative of r with respect to t. Exactly right, because now you're taking the derivative of that inside function. Okay, now there's some stuff we can simplify there, JJ, right? Because I've got a 3/3. So that whole thing simplifies down to what?
4 pi r squared dr dt.
Interesting. Okay, so what do you notice, Fallon?
Sorry, could you repeat the question?
What do you notice about this new equation that we just got?
Well, we now have dr over dt, which we
don't have, right? And we
yeah.
don't have a way to find that, right? What else do you notice? Anything?
Well, we have 4 pi r squared, which is equal to a.
Right, so we have some information that's going to correspond with each other, right? We have our a now into this equation, so we'll keep that in mind in just a second. Okay, let's go to Ben. Ben, what would the derivative of that right-hand side equation be? Of our a equals, what would the derivative of that be with respect to t?
dA over dt would be equal to 8 pi r dr dt.
Okay, so this is all of the information I have right now. Okay, I've got a dv over dt equals 4 pi r squared dr dt. I've got a dA over dt equals 8 pi r dr dt. Okay, what Fallon noticed is now we have dr dt's all over the place, and I have no dr dt in my list of information. Okay, does everybody have all of this written down so far? I hope so. Yes, thumbs up. I'm going to send you into small groups. I want you to talk about any strategy you can think of to do next. Okay, so you're going to be in those same breakout rooms you've been in before. I just opened them up. I'm going to give you a couple minutes. Talk about it. Everybody unmute. Go to those small groups now.
Times dr over dt, we were able to plug in 60 pi, or we started to plug in values that we were given in order to find dr over dt.
So you use this equation to find dr dt. So we weren't given dr dt, but we know we need to use it, right? So you could use your given information in order to find that dr dt. So what did you plug in, Augie?
So 60 pi equals dv over dt equals 4 pi, and then we were given r is 4 inches, so 4 squared times dr dt. And then
okay, keep going from here.
Solved it for dr dt, which the pi's canceled out, and we got 15 over 16.
Okay, so you're doing 60 pi over this like 4 times 16 pi, right, equals dr dt. And you got what final answer?
15 sixteenths.
15 over 16?
Correct.
Equals dr dt. Okay, so what did you do next with that? And you might not have gotten there, Augie. Actually, let's go to someone else. Let's go to someone I haven't picked yet. Justice, what would you do with that?
Yeah, so after that, you could plug in your dRdt into the surface area with dA over dt. So you get d over dt equals 8 pi times 4 times 15 over 16.
Okay.
And you get 32 pi times 15 over 16. And then you could
simplify our 32 and 16 maybe?
Yeah. Shoot. Would you take out a 32 and you get
so 32 divided by 16 is 2, right?
2,
so,
yeah. So 15 pi over 2?
Nope, not quite. So 32 divided by 16 is 2, not 1/2. right? So you still have a 2 up top, so a 2 times 15 times
so
pi.
30 pi. So 30
There you go.
pi.
Perfect. Okay, now, Justice, what kind of units would that be in?
Surface area.
So it's an area over a
squared.
time. Inches squared, perfect.
Inches squared, yeah.
Per what?
Per second.
There you go. So remember, the top thing needs to match whatever that variable is. So if it's a change in area, that's an area. Over a change in time, that's a time. So I get inches squared over seconds. Okay, so this had a couple more steps than our basic like setup, but it was the same idea. We identify what's given, right? We identify our equations, those were given to us also. We take derivatives of those equations. Usually we have one, but this case we had two, and then we had to plug stuff in. So I think it was Fallon at the beginning that said, well, couldn't we just like manipulate that first equation and then come up with an A equation inside of it? So you could have, but it actually doesn't make the problem easier because you end up having product rule and you end up still having all those unknowns and stuff. It's just within one equation instead of two. I think this is the easier approach. Okay, are there any questions on this problem? Okay, let's go to the next one. So the next one says the size of a cylinder changes with time. If the radius increases at 2 centimeters per minute and the height decreases, so decreases is a very important word when we're talking about related rates. So it decreases at 8 centimeters per minute. At what rate, Justice, you're still unmuted. And make sure your mask is up. Goober, thank you. At what rate is the volume changing when the radius is 1 centimeter and the height is 5 centimeters? Would like you to take a second, write down all your given information. Note the decreases word. It's going to be important. Let's go to Ryan. Ryan, do you have some given information for us?
Yeah, so we know that dv over dt should equal, dr over dt equals 2.
So dr over dt is equal to 2. So that's talking about the radius increases at 2 centimeters per minute. Okay, great. Keep going.
And we know that dh over dt equals -8.
Good. Why is there a minus on that one, Ryan?
Because it says the height is decreasing, not increasing.
Exactly. That's very important. So when something is decreasing, that means the derivative is negative. It's a really important thing to remember when we're reading these problems because it's easy just to pull out the numbers and forget the negative. It changes the whole thing. Okay, keep going.
So we know that our r is equal to 1 and our h is equal to 5.
Okay, and what's the piece of information we're looking for, Ryan?
So we're looking for dv over dt, where v means volume.
Correct. So it is really important to include whatever you're looking for because it helps you come up with an equation. Okay, so my variables now are v, r, and h. I'm dealing with the volume of a cylinder. You'll notice they did not give you the equation for the volume of the cylinder. Here's why. The volume of a cylinder is just base times height. What is the shape of the base of a cylinder, Mateo?
A circle.
A circle, right? So the area of the base, a circle, times the height. That's the volume of a cylinder. So a volume of a cylinder is pi r squared times h. We have a dr dt, we have a dh dt, we have a dv dt, we have an r and an h. We have almost all the information we're possibly going to need. But when you take this derivative, you have to be extra careful of something. I would like you to try to take this derivative now. Be mindful, I'm giving you a hint. Be very careful of something when you take this derivative. Think about what I could be referring to. All right, Chirag, what do you think I'm talking about when I say be very careful taking this derivative?
Product rule?
Product rule, exactly right. So I have a function, pi r squared, times another function, h. So I have to use product rule in order to come up with this. Okay, so I'm gonna have my little a and my b chart, my a prime and my b prime. Chirag, what's gonna go in for my a?
Pi r squared.
How about my b?
H.
What's the derivative of pi r squared?
I got 2 pi r dr dt.
Fantastic. And the derivative of h?
dh dt.
Perfect. Okay, so let's plug all of that information in. Chirag, what did you get for your derivative? On the left side, what would you write?
dv dt equals pi r squared times dh dt plus h times 2 pi r dr dt.
Fantastic. I would like everyone to try to solve from here. Everyone should be trying to solve from here. Is this what you guys got? Thumbs up. Ethan Balliser, what units should go on this?
Centimeters cubed per minute.
Centimeters cubed per minute. I agree. We're dealing with a change in volume, centimeters cubed. We're dealing with a change in time, minutes. Be careful. A lot of you guys like to just assume it's seconds or feet or something like that. This one had centimeters and minutes, so we get centimeters cubed per minute. Okay, we are just about out of time. Let me go ahead and